So, if you've ever worked with a single decision tree in machine learning, you know it's a pretty powerful tool, right? But what happens when you go from just one tree to an entire forest? That's what we're going to dive into today, ensemble methods, to see how combining models can unlock some dramatically better results.
Seriously, just think about this for a second. One brilliant expert, they might have blind spots, maybe some biases, or they could just get fixated on the wrong details. But a diverse crowd, well, they tend to cancel out each other's errors, and their collective guess is often shockingly accurate. This is the core idea we're going to explore today, the wisdom of crowds before machine learning.
So our story starts with the single decision tree. It's a fantastic model, don't get me wrong, but it has this one fundamental flaw. It's a perfectionist. It tries so hard to get everything right on the data it's trained on that it ends up learning all the wrong lessons.
And this perfectionist problem, it has a name: overfitting. Imagine you're studying for a test. Instead of actually learning the concepts, you just memorize the exact answers to the practice questions. You'd get a perfect score on that practice test for sure, but you'd probably bomb the real one because the questions are different. That is exactly what a single decision tree does. It memorizes the noise in the training data and then can't adapt to new information.
And here is that problem in action. Look at the scores for our single tree. On the training data, the stuff it already knows, it gets a perfect 1.0. But look what happens when we show it some new validation data. The accuracy just plummets. That gap right there, that is the classic signature of overfitting.
Okay, so how do we fix this flawed perfectionist? We bring in a team. This is where our hero, the ensemble method, enters the story. Instead of relying on one over-specialized model, we're going to combine the predictions of many different models to get a much more robust and accurate result. This quote really just gets right to the heart of the solution. By averaging out the predictions of a bunch of different trees, we essentially filter out the noise that any one single tree might have obsessed over. It's the wisdom of crowds principle coming in to save the day.
So, we know we need a team. And in the world of machine learning, there are two superstar strategies for building these teams. So let's get properly introduced to our two star players, random forest and gradient boosting.
Now, both of these methods are chasing the same goal, higher accuracy and less overfitting, but they go about it in completely different ways. You can think of them like two rival coaches with totally unique philosophies for building a championship team.
Let's break down their core strategies. Random forest, this one acts like a council of independent experts. It builds a whole bunch of different trees at the same time, each one looking at a random slice of the data, and then they all just vote on the final answer. This is called bagging, and it's brilliant at reducing variance, which basically means the model isn't so sensitive to tiny changes in the training data. Now, gradient boosting is different. It's more like a team of specialists that learn from each other. It builds one tree, finds its mistakes, and then builds a new tree specifically to fix those errors. This step-by-step process is called boosting, and it's incredible at reducing bias, which makes the model's core predictions more accurate.
So here's how random forest actually builds its team. First, it samples the data, creating lots of different random subsets. Then, it builds a totally unique tree for each one of those samples. Now, to make sure the trees are truly different from each other, it also limits each decision to a random subset of features. And finally, all the trees get to vote and the majority prediction wins. It's a really simple, powerful, and very efficient way to do things. Now, contrast that with gradient boosting's sequential approach. It starts out with a simple, kind of weak prediction. Then it identifies all the errors and builds a new little tree whose only job is to correct those specific mistakes. It adds this new corrective tree to the model and then just repeats the cycle, with each new tree getting smarter by fixing the errors of the one that came before it. It's a very methodical and incredibly powerful process of improvement.
All right, that's enough theory. It is time for a showdown. Let's put these strategies to the test with a classic machine learning challenge.
So here's the setup. We're using the famous iris dataset, where the goal is to classify flowers into one of 3 species based on their measurements. And in the ring, we've got our original, overfitting single decision tree, a random forest built from 50 trees, and a gradient boosting model also made of 50 trees.
And the results are in. This single tree, you see it right there, shows that classic overfitting problem. Perfect training score, but a big drop-off on new data. But look at the ensembles. Their training and validation scores are so much closer together, which tells us they're far more stable and reliable. And would you check out the random forest? It gets a perfect score on the final unseen test data. I mean, that is incredible generalization.
This bar chart really just makes the final verdict crystal clear. On the data that truly matters, the test set that it has never seen before, the single tree is lagging behind. Gradient boosting does better for sure, but random forest just knocks it out of the park with a perfect 100% accuracy. That is the power of the ensemble.
So what is the big takeaway here? Why do ensembles consistently win? Well, our showdown gave us the answer. They are simply stronger together. So let's just summarize the key advantages. Ensembles dramatically reduce overfitting because the errors of all those individual models get canceled out. This leads directly to higher accuracy on new data. They're also far more stable. Shuffling your training data around a bit won't drastically change the model. And as a bonus, they often give you more reliable insights into which features are actually driving the predictions.
You know, we've just seen how a forest of models can easily beat a single tree. It really makes you wonder, what comes next? How do we build even smarter, more effective teams of models? That's a question that drives this entire field forward, and it's a pretty exciting one to think about. Thanks for